My name is Carl Anthony, and I work in the automotive industry in Detroit. Sometimes that work encompasses future vehicle technology, and that's what we talk about here, for the most part anyway. This is AutoVision News Radio. A pleasant surprise at AutoSense Detroit recently when we met Hyperspec AI for the first time. Sravan Puttagunta is the founder and chief executive officer of the company, where he is executing on a vision to achieve autonomous driving at scale by enabling superhuman perception in self-driving vehicles. Now, previously, Sravan was the CEO and founder of Civil Maps. Prior to that, he developed video fingerprinting at Samba TV as the lead algorithm developer and has authored several patents on the topics of cognition, mapping, video fingerprinting, point cloud fingerprinting, and mixed reality services. Sravan holds a master's in electrical engineering and computer science from the University of California, Berkeley, and a bachelor's in computer engineering from California State University, Chico. He joins us today on AutoVision News Radio. Sravan, welcome.
Thanks, Carl.
You are the CEO of Hyperspec AI. So first, can you tell us just a little bit about who you are and your background and areas of expertise, and then what Hyperspec AI is focused on right now?
Ever since school, I've been an engineer who's been focused on computer vision. And my early work has been focused on helping the founders at Samba develop a automatic content recognition algorithm for linear broadcast TV. I've taken some of those learnings to build my own company, which was Civil Maps in 2015, focused on high definition mapping for self-driving vehicles. And we engaged with a lot of automotive customers, and I've taken a lot of learnings from the industry. And we realized that there is a huge opportunity to address a market gap by building real-time maps. And that's what we're doing at Hyperspec. We are focused on giving vehicles the ability to perceive, see, and think and act like humans do, especially as it pertains to spatial reasoning and spatial context. The way we see our role playing is we are solving a crucial problem that allows autonomy to scale. And the way we're solving it is we're studying how biological systems deal with complex environments and figure out how to navigate those complex spaces. And we're trying to reproduce some of those capabilities in the context of self-driving cars or cars with driver assistance systems. So firstly, I guess the first question to ask is, how do humans perceive? How do we understand the world and how we interact with the world? Humans don't have a blueprint of all the geometric shapes that they could potentially run into as they're walking around in the environment, but instead we're able to look at the vision information that we're capturing with our eyes in real time and use our brains to process the information and contextualize what we're seeing. The difference with cars today is that they're being spoon-fed the context through a database that's called the high definition map. And this context describes everything to the car, and simply the car has to follow the rules of the road and drive within the constraints that are predefined. But the problem with this approach is this HD map coverage is only on the highways and in limited cities. So how do you go from highway-only autonomy to highway to driveway autonomy? You have to build a more scalable perception and spatial reasoning capability in the car. And that's where human and biological systems in general, we've solved this problem through biology. And having the ability to reproduce the same capability in the car is the core focus at Hyperspec. And if we crack that problem, and if we're able to empower the car to replicate the same capability, then we can dramatically accelerate autonomy and the availability of autonomy so anyone can use it no matter where they live.
Along those same kind of guidelines, I have another colleague and friend in this automotive industry. She talks about how you have to look at cognitive brain science and the number of cortical neurons in our brain versus, say, other animals. And one of the things she talks about is that when you boil all of that down, whether it's animals or humans, we're very good at improvising. And that is one of the difficulties with autonomous vehicles, is that they're not as good at improvising like we would be as humans. In my understanding, I want to make sure I'm understanding you correctly. You're saying something very similar to that we've got a machine and then we have a human, a biological system, and there are advantages to the biological system, no matter how amazing the computer may be.
Definitely. So one way to think about it, when humans start exploring 3D spaces, it's when we're very young. And we have a feedback loop, whether it's a signal where we like fall down, or our parents are talking to us and telling us not to do something. There is some reinforcement happening. But what we do as children, we're pretty much unconstrained in the things we try. And then over time, we build something called the safety bubble, which is our sense of safety. And then as long as we're within the constraints of the sense of safety, we can dynamically adjust the things we try, so that when we feel more safe, we're more flexible on what we're willing to try. When we feel less safe, then we're more conservative, take more time making certain decisions. Additionally, I think if you think about perception, you can break it up into two categories. You have the sort of subconscious, which is, okay, I don't really care what this object is, but I do recognize that there's an object that's coming at me really quickly and I need to get out of the way. That can run on autopilot without you actually understanding the context of what's happening. At the conscious level, you realize that, okay, that's a semi-truck, or that's a car, or that's a bicyclist. And we need to then plan around how to interact with this object. And both of these signals are firing at their own frequencies, and they have different levels of cognitive load. So biological systems have figured out that this type of decision-making has to be asynchronous and it has to be unconstrained, and these things have to operate independently. Whereas in a self-driving stack, the HD map basically gives you a virtual train track, and everything has to follow the logic that's predefined and pre-coded, and it's very rigid. So evolving the autonomous stack from relying on the HD map to something that's more real-time, that's more flexible, that allows the car to explore things in an unsupervised way and provides it feedback with the safety envelope, which constrains what it can or can't do, is a step towards mimicking how we as humans and other biological systems are able to deal with spatial navigation.
Sravan, this is one of the reasons why I was so glad to meet you and your team at AutoSense. So I've been in automotive journalism for a good portion of my career. And back in, say, 2015, when I really started writing about autonomous vehicles, I had a very naive viewpoint. And I thought, well, okay, sure, they're going to be here by 2020 or 2025 or whatever the case may be. So I really bought into the hype. And these were conversations, the conversation that we're having right now. We weren't having that conversation back in 2015, at least not that I was aware of. It seemed pretty cut and dry. Autonomous vehicles are here. There's some ADAS technology. We should be able to mass produce it in the next 5 years, and autonomous vehicles are going to be here before you know it. And then we started to really figure out what it took to develop an autonomous system. And this biology conversation, this is wild. It's exciting. It's cool. But it just goes to show you just how difficult it is to develop an autonomous vehicle.
Yeah, definitely. I think in 2015, there was tremendous hype around the technical capabilities. If you think about a roadmap as a sequence of milestones, that's probably the wrong way to think about it. It's a sequence of decisions. So once you reach a certain milestone and you've seen the outcome, then you do the planning for the next iteration. And what happened there is we had a sequence of milestones where everything falls into place perfectly. And we all of a sudden in the year 2020 will have autonomous cars. But what really happened in the real world is that we unpacked each one of these problems, and we discovered the complexity of the problem when we were 8 feet deep. And then we uncovered new problems that we need to solve in order to make this technology work reliably. And then we're starting to see that some of the bottlenecks cannot be solved through brute forcing because we're limited by people, we're limited by how much data we can backhaul. So moving the intelligence from a centralized location like the cloud to the edge, and then investing more time and energy into the hardware acceleration within the car and starting to mimic some of the capabilities that humans have is, I would say, a theme that really has taken off since 2019. And that's what got me really excited to start Hyperspec, because I think the timing of the market is really important to introduce the technology. Had we introduced this technology in 2015, I think our impact in the market would have been much less.
So let's go to your website for a second. On the Hyperspec AI website, you highlight 4 main points: Vision SDK, SLAM pipeline, hardware acceleration, and validation infrastructure. Can we go over each of these 4 things and then break down what they mean for the automotive industry?
So the Vision SDK is essentially a piece of software that a car manufacturer or tier 1 supplier can license from us, which would give the car the ability to construct a real-time map on the fly by processing the sensor data. And the goal is to create this map with a certain resolution and certain fidelity that is a plug-and-play replacement for an HD map. Like, we don't want to have the car manufacturers completely retool their self-driving stack because we changed the standard from an HD map to an online real-time map. We want them to be able to seamlessly integrate our solution. So the Vision SDK is going to be optimized to give the car manufacturers and tier 1 suppliers a seamless integration process. The SLAM pipeline is essentially our ability to take sequential sensor data. So for example, multiple video frames over time, and compute the relative change in position or the orientation of the vehicle. And then also use that same data to compare with orthogonal third-party data like aerial imagery to help the vehicle position itself. The reason we chose aerial imagery is that it's available in most of the US cities, and it's being used by other industries like insurance, real estate, solar, city planners. So we don't have to create that infrastructure from scratch. We're actually using the data that a lot of other industries are using. So we're leveraging the economies of scale, unlike HD maps, which are only available on 2 to 3% of roads.
Right.
Hardware acceleration is very important because in a real-time system, for the map to be usable, it has to be created in less than 50 milliseconds, and it has to be refreshed at least 20 to 30 times per second. So that means the latency, when the data is generated to when the map is created, has to be very low latency, and it has to be frequent enough that the car can react in the same way a human can. And then lastly, the validation infrastructure is important for our customers to believe that the technology works. So the way we actually test this is we have our sensor kit, which is co-mounted with the customer's measurement card, which they use for ground truthing. And then we can make apples to apples comparison between our system and theirs. And once those 2 results converge, we co-author the report with the customer, and we're able to actually safety certify the technology, in which case we can start the integration process with the car and not just use a retrofit kit.
97% of roadways are inaccessible to autonomous vehicles because of the limited coverage of high-definition maps. 97% of roadways are inaccessible to autonomous vehicles because of the limited coverage of HD maps. From your perspective, why is this an important statistic to consider? And what do you think is the most effective way as an industry we can address this?
Sure. So if you look at the US road network, there's 6.6 million kilometers of roads, of which roughly 500,000 consist of highways. And there's a couple cities like San Francisco, Pittsburgh, Phoenix, Mountain View that have self-driving infrastructure where they've been mapped by these robotaxi companies. So if you add up all the highways and you add up all these cities, that's roughly 400,000 to 500,000 kilometers of roads, which is 5% of the overall road network that we have. And then if you go to other countries, which maybe don't have as much autonomous research, that number would be even less. So this technology is not really available to a lot of folks in the world due to the fact that creating these maps requires an army of humans to manually label the data. And a lot of the base map companies and map crowdsourcing companies have thousands of folks working in markets where labor costs might be cheaper, like Asia, where the labeling is happening, and that label data is then used to create the map. So that process, yes, you might save 5 to 10x the cost by having the label data done in these markets. But once you reach a certain scale, even that cost saving becomes a bottleneck. So the only real path forward is to create a real-time map that can give you the same level of context that you'd otherwise get from this database that's predefined. And the ability to do that has to be done on the edge by processing the sensor data. So yes, we need to increase the quality of the sensors. We need to make sure the perspective of the sensors gives you a full 360 perspective around the car. We need redundancies in the car in terms of the number of sensors and the computation. And then we need to have some really smart algorithms process the sensor data to create that scene context. And I would say that the motion planning algorithms, the actuation algorithms, the sensor fusion algorithms are fairly mature at this point, and they've been tested in the smaller environments. And so going from one city to the next 100 doesn't dramatically change the way these algorithms will function. What will change is availability of data to power that spatial reasoning and defining the rules of the road. The real-time mapping is solving for that key bottleneck, which enables us to now go from those 3% road coverage to that, complete comprehensive road coverage, where those 97% of the roads become available to self-driving technology.
When you were in London, can you share some key insights and takeaways from the training data that you collected while you were there?
Yes. I think the main point there is, driving behavior is different. For example, a solid white line is not something you should cross in San Francisco, but you're expected to cross it in London. So the rules of the road are, you could say, domain specific. And having an HD map define the rules of the road in California and expecting that standard or specification to work worldwide is not scalable process. So you need a way to observe driving behavior in each city and localize the contextualization to be specific to the environment where you're operating based on something called fleet learning. And the concept of fleet learning is that initially you deploy this system as a driver assistance system where the system is being monitored by humans and it's attempting to navigate complex 3D road networks. As it makes a mistake, the human might disengage the vehicle, and that acts as your feedback loop or reinforcement learning mechanic to solve for that edge case. And so that feedback loop can then be used to create a universe of edge cases where you have all the different scenarios that you need to handle within a specific geographic region. And then the cloud infrastructure that really is used to create label data and is used to retrain the models will process those edge cases based on the geographic location where they were created and publish a new model back to the car, which gives you a domain-specific driving behavior.
How did you think up this concept for Hyperspec AI? The whole time we've been talking, I've been saying to myself, where do you get the idea to do something like this? This is so neat, Sravan. Where did this inspiration come to you to do this and to start Hyperspec AI?
I think the crucial experience I've developed interacting with the automotive industry and seeing the bottlenecks of the traditional approach, which uses high definition maps and the annotation teams. Firstly, I saw the lack of appetite to finance map creation in every city, and I didn't really see any viable solution being proposed within the market on how to tackle this problem and expand the coverage of those HD maps. So I started looking at a first principles approach to solve this problem. And the realization I've come to is the reason maps were used. It was essentially a stopgap solution in the DARPA challenge. During the DARPA challenge, computational capacity in the car was not that great. And to circumvent that bottleneck, the competing teams created the high definition map to describe the environment to the car. And the best performing teams had a high definition map. The teams that were relying on real-time mapping didn't finish the race, or they didn't perform well in the race during the DARPA challenge. And so because of that, a lot of the people that won this challenge went on to become the thought leaders in the autonomous space. They started companies, and that sort of became the norm. Since then, no one really has taken a first principles approach to redefining the problem statement, I would say until 2019. And then a couple companies emerged in the space, sort of defining the problem statement in the same way. You have Tesla, which is saying that, hey, we can create a 360 representation and define the problem statement for creating this real-time representation of the scene, so we can replace HD maps. You have another company called Wave, which is using unsupervised machine learning that is using a slightly similar approach, but they're vertically integrated end to end. So I would say Hyperspec is one of the few companies that is focused on enabling this type of capability in the traditional AV stack, where it's not an end-to-end neural network, but rather a loosely coupled modular architecture that the OEMs can use to essentially create a drop-in replacement for the HD map without having to retool or re-architect their entire AV stack. And that's kind of why we are uniquely placed and motivated, because I think that's where the greatest need is within the market, as Tesla and Wave and other companies validate this approach.
Sravan, I'm so glad that I was able to meet you and your team at AutoSense, and we were able to then sit down and do this podcast. Thank you for your time, for sharing your industry expertise and thought leadership from all of us here at AutoVision News. We want to wish you the best of luck going forward, and thank you for being with us today.
Thank you, Carl. I appreciate the opportunity, and it's very nice to meet you.
To learn more about Hyperspec AI, visit the company's website, hyperspec.ai. That's hyperspec.ai. You can follow Hyperspec AI on LinkedIn and keep an eye out for the Hyperspec AI team at any number of upcoming industry conferences where you can connect with them in person. In Detroit with Sravan Puttagunta, I'm Carl Anthony, AutoVision News Radio.